Hello students, let us discuss the concept of hybridization with some examples. Let us take an example BeCl2. In order to do the hybridization for a molecule, first of all we need to identify the central atom. In BeCl2, Be is the central atom. The atomic number for Be is 4, so its electronic configuration is 1s2, 2s2, 2p, 0. This electronic configuration is called as ground state electronic configuration. In the case of Be, the outermost shell is the second shell here. So since there is no electron in the 2p, so I have written here it is 2p0, 1s2, 2s2, 2p0. For the case of bonding, the inner electron have no role. So I am not writing the electron of 1s while making the orbitals. So while making the orbital for 2s, single box is made, and for 2p, 3 boxes are made. So 2 electrons are there in the 2s, which is represented here as arrow, and there is no electron in 2p. That means it is a 2p is the vacant orbital. In this molecule, the 2 chlorine atoms are combined or get bonded. So in order to share the electron of chlorine, single electrons are required. So in order to share the 2 chlorine atom, 2 single electrons are required. But here the electrons are paired. So one of the electron from 2s get promoted to the vacant 2p orbital to account its divalency. So in the excited state, we can say that one of the electron of 2s is promoted to the vacant 2p orbital. So now we can see there are 2 single electrons. So that can be easily shared with 2 chlorine atoms. But before the sharing, these orbitals, that is one s orbital and one p orbital, it get hybridized. So this hybridization is called as sp hybridization. So one s and one p get hybridized. So it results in the formation of 2 sp hybrid orbitals. As we have already discussed, how many number of atomic orbitals are combining, that much number of hybrid orbitals are formed. In this case, 2 atomic orbitals are combining, that is s and p. So it results in the formation of 2 sp hybrid orbitals. The 2 sp hybrid orbitals, these are oriented in opposite direction, forming an angle of 180 degree. So the beryllium having 2 sp hybrid orbital, that is this and this. These are the 2 sp hybrid orbital for beryllium, which are oriented in the opposite direction, forming an angle of 180 degree. So its shape is linear. Now these 2 hybrid orbitals overlap with the p orbital of 2 chlorine atoms. So there will be a formation of a sigma bond, because here there is a head-to-head overlapping, that is sp hybrid orbital of beryllium and 2p orbital of p orbital of chlorine. There is an overlapping. And when you look at this one, this type of overlapping is called as head-to-head overlapping. So it results in the formation of a sigma covalent bond. So look at this structure carefully. The green color shaded orbital, that is a hybrid orbital of beryllium. That is 2 hybrid orbitals are there. And the orange color orbitals are the p orbital of 2 chlorine atoms, which is represented here. So there is an overlapping between the p orbital of chlorine with sp hybrid orbital of beryllium. that result in the formation of sigma bond. Similarly, one more sp hybrid orbital of beryllium is overlapped with the p orbital of another chlorine atom, which result in the formation of sigma bond, because here the overlapping is head to head overlapping. So this is nothing but shown here. That dotted box shows that this orbitals, that is s and p orbital, get hybridized. Now these orbitals, which is now it is called as sp hybrid orbitals. These two orbitals are now called as sp hybrid orbitals. It is not called as s or p. It is a combination of both s and p. So it is called as sp hybrid orbital. Now these are the sp hybrid orbitals, and each sp hybrid orbitals is overlapping with the two fluorine atoms. So this is makes the geometry of this molecule as linear geometry because of the angle 180-degree angle. So what we can say that for this molecule, the hybridization is sp hybridization, that is due to the one s orbital and one p orbital which get hybridized to form two sp hybridized orbital. And these two sp hybrid orbitals are oriented in the opposite direction, forming an angle of 180-degree. So better in the simple way, we can make this geometry in this way, that is BeCl2, and the angle between them is 180-degree. Let us discuss another example, BCl3. BCl3, here the central atom is B. The ground state electronic configuration is, that is 2s2 2p1. I am not mentioning 1s2 here. 2s2 2p1 are the outermost electronic configuration for boron. That is the ground state electronic configuration. Here 3 chlorine atoms are there. So 3 single electrons needed for central atom boron. So one of the electron from 2s get promoted to the vacant 2p orbital. So in the excited state, you can see here, now there is only single electron in the 2s, and in 2px and 2py there is one single electron. So we can say that there are 3 single electrons are there in the central atom boron. These orbitals, that is 1s orbital and the 2p orbital, get hybridized. It results in the formation of s, because 1s and 2 p's are involved, so sp2. So this type of hybridization is called as sp2 hybridization. Geometry of sp2 hybridization is trigonal, which is shown here. The orange color shaded orbitals are actually the hybrid orbitals, that is sp2 hybrid orbital of central atom boron. Now here 3 orbitals are combining, that is here 1, 2, 3. 3 orbitals are combining, so 3 hybrid orbitals are formed, that is shown here. So these hybrid orbitals, that is, this is sp2, 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 3 sp2 hybrid orbitals are formed. It overlap with the p orbital of 3 chlorine atoms, and this type of overlapping is actually head to head overlapping. Look at the overlapping here. It is a head to head overlapping, that is the overlapping between the sp2 hybrid orbital of boron with the p orbital of chlorine. For the case of chlorine, why the dumbbell shape is made? Because the p orbital is a dumbbell shape. So for chlorine, the p orbital electron and the sp2 hybridized orbital electrons are sharing. So the geometry will be in this way. So here there is a overlapping between the sp2 hybridized orbital of boron and p orbital of chlorine. So there is a formation of a sigma bond. So there is a formation of a 3 sigma covalent bond. So in easier way we can make the structure, that is B is the central atom and they have trigonal geometry because of the angle 120-degree angle. So this is the hybridization for BCl3. Now let us talk about another example, methane. In methane, the formula is CH4, where the central atom is carbon. The ground state electronic configuration for carbon is 1s2, 2s2, 2p2. So that we have made the boxes here. 1s is not taken here, only the outermost shell is considered. So 2s2, 2p2. In order to form the bond with 4 hydrogen, 4 single electrons required. But when you look at the ground state for carbon, only 2 single electrons are there. So one of the 2s electron get excited or promoted to vacant 2p. Here there is a vacant 2p orbital. So one of the electron from the 2s get promoted to the 2p. That is a vacant 2p. Now in the excited state, when you look at here, there are 4 single electrons. So now these will undergo hybridization, that is 1s orbit and 3p orbit. How it is 3? 1, 2, 3. 3p orbital get hybridized. So this type of hybridization is called as sp3 hybridization, because this hybridization, it involves 1s and 3p orbitals. So total number of hybrid orbitals formed here, that will be equal to 4. Why it is equal to 4? 1s and 3p. When you make the sum, 1 plus 3, 4. So total 4 atomic orbitals are combining. So there will be formation of 4 hybrid orbitals. So these 4 hybrid orbitals for carbon atom is represented here. That is the orange color shaded orbital are the hybrid orbitals. What we call this hybrid orbital? That is sp3 hybrid orbitals. So 1, 2, 3, 4. These are the sp3 hybrid orbital of carbon. 4 sp3 hybrid orbital is overlapping with a s orbit of 4 hydrogen. Now look at here, why it is made spherical here? Because in the case of hydrogen, the electron is in s orbit, that is in 1s. So the electron in the 1s of hydrogen orbital, that is 1s orbital of hydrogen, is overlapping with the sp3 hybrid orbital of carbon. So spherical shape you have to make for hydrogen orbital, that is 1s, and this is actually the orange color shaded one is for the hybrid orbital of carbon. So there is an overlapping between the hydrogen and the sp3 hybridized orbital of carbon. It results in the formation of sigma bond, because here there is a head-to-head overlapping. So it results in the formation of 4 sigma bond. The geometry is tetrahedral. So it is easy to draw the structure in this way. That is carbon and 4 hydrogen, that is tetrahedrally arranged. So this is the geometry for methane, and this sharing is shown here. That means the 4 hydrogen and the 4 sp hybrid orbitals that is overlapping is shown in this way, and in diagrammatically it is shown here. So this is the hybridization of methane. Let's discuss another example, SF6. SF6, in this case, the central atom is sulfur. So first we need to write the ground state electronic configuration. So that is the outermost shell here is the third shell. So 3s2, 3p4. There are 2 electrons in the 3s and there are 4 electrons in the 3p. Now here 6 fluorine atom is getting bonded with a one single sulfur. So 6 single electrons are needed. So in order to have a 6 single electron, the paired electron get excited, it get promoted to the vacant 3d orbitals. Like here one of the paired electron get promoted to this 3d orbital. At the time there will be only 4 single electron, but there are 6 fluorine. So one more paired electron, that is from S, get promoted to the vacant 3d orbital. So what will be the excited configuration? That will be this one. That is due to the excitation of a paired electron from 3s and 3p to the vacant 3d. Now in the excited state you can see that there are 6 single electron. So these orbital, that is 1 s orbit, there are 3 p orbitals, so p3, and there are 2 d orbitals. So they get hybridized. It get hybridized to form sp3d2 because 2 d's are there. So it form sp3d2 hybrid orbitals. The geometry of sp3d2 hybrid orbital is octahedral, which is easily we can make in this way. There is single sulfur and there are 6 fluorine atoms. 6 fluorine atom, from this 4 fluorine atom and the single sulfur is on the same plane. One fluorine is above the plane, the other fluorine is below the plane. So this is geometry is for SF6. This geometry is called as octahedral geometry. Is called as octahedral geometry. So the sp3d2 hybridized orbital of the sulfur, that is 6 sp3d2 hybrid orbitals are formed, which is represented here. So these will overlap with the p orbital of 6 fluorine atom. So it attains to the stability. So that is the sp3d2 hybridization. So in the same way you can try the example PCl5. All of you try this example PCl5 and IF7 in the same way, depending upon the conditions which we have discussed here. First you need to write down the central atom, its electronic configuration. Then you need to do the excitation and depending upon the number of orbitals of S, P and D involved in the hybridization, the geometry and the hybridization will be based on that concept. So all of you try the example IF7 and PCl5. So it was clear that the d orbitals can also be involved in the hybridization. So there are different type of hybridization like dsp2, sp3d, sp3d2, sp3d2, d2, sp3, where the d orbitals are involved in the hybridization. The examples of these like the case coordinate complexes. In these examples there is an hybridization in which there is an involvement of d orbitals also. So these examples will be discussing in the next year in the chapter coordination complexes in 12th standard. So all of you try these examples also. BRF5, PCl5. So these have a geometry in which the hybridization is involving the d orbitals also. So this is all the different examples. So hybridization is quite important topic. So all of you practice these problems, that is the molecules, different type of molecule, by using the orbital diagram which we have discussed here. So this is all about this video. Have a nice day.